Hello, welcome back to the stream. Just maybe another half an hour, 45 minutes. Let's go back into it. Okay, let's see. So we were playing with the arbitrary instances so that we could see what kind of arbitrary graphs the arbitrary instance or the gen instance that we created for our graph created. So let's see if we can, let's for instance create a graph event and see what that looks like. And maybe prime, and I think I missed an int here, and then see what that would look like here. Okay, so the empty graph gets removed, and yeah, we have what looks like ints. So I think that gives me some confidence that these examples, that our arbitrary instance actually works. Let me try a big one though, like a big Boolean one. Because I think the size here didn't do it, but what if I say resize 10 of a graph Boolean? How's that's gonna work out? Okay, what am I doing? There we go, and second. Might be quite big actually, but it's not. So I'm not sure whether this is actually working. I think maybe I need to also do it here. Yeah, I'm not sure I know how to use the size properly, because earlier I actually got a bigger graph by changing the seed rather than changing either the resize or the size here. Right. Yeah, also if I run gen after resize 10, that shouldn't change anything. But then it's possible that the seed makes this run out at some point. So I should try to create a big one and see if I can shrink it or make it smaller. This is a tiny one. This is also just a leaf. And this is pretty tiny too. Okay, although this seems to have at least 1, 2, 3, 4 layers to it, I think. So let's try and play with that a bit and see if I can, well, see if resizing to 2 outside makes any sense. Looks like it does. So if I resize to 3, I would expect to have, well, It's not clear actually. Yeah, yeah, that makes sense. Well, 3 3 or 2, it's not easy to say. What if I say 4 here? Seems like it does what it's supposed to do. What if I start with 0 here? Maybe I should have started with 1. Yeah, same thing. Actually, yeah, this is a different graph though. Well, actually, interesting the way this simplifies. I think this might be a good example to try and canonicalize here. So to be honest, I'm not super confident about how this is working, but it's a little bit tricky. Because changing the size seems to be generating different graphs, and I don't know if that's how it should be. But I'm saying that this could be a good example for for like a normal form, because here false true true false I think should be basically the fully connected Boolean graph. But this simplification here is not necessarily the one we want. It seems like this is not distributed over false true. Depends a bit what we want. It's not clear. Do I want to do that now? I think it's part of the important stuff for me to understand here. So let's say, let's try. So let's see if Alga, well, what am I doing here? Let's see if the Haskell version has the normal form in it or not. Let's go look at the add package, and actually I want to make sure I'm using the latest version graph, and then we have simplify. We do a given expression according to the laws does not compute the simplest possible expression, but uses heuristic to obtain useful simplifications. Okay, and specify. So it's not clear whether there is a function for creating a normal form here. Normal is not there. Canonical. Adjacency map is the canonical graph representation. So what's EQ like? EQ is EQR, and EQR just converts them to the adjacency maps. Okay, let's take a look at the adjacency maps. to adjacency map. That's what EQ is. So, I mean, yeah, that's interesting. I could actually test equality of false, true, false with, I suppose, false, true. Is that the simplest version? Let's see what two adjacency map of. Okay, that doesn't work. Unknown value. Okay, can import that from a regular adjacency map. No, it's not what I wanted. Undirected. Is it not imported? Exported? And that must be from the module. No, it's not. So is it from internal? It's not. Okay. I see, it's just from graph. And is it exported? It is not. Well, that's not good. Okay. And can import this now from graph. Except we don't have a show instance for them, but we'll build one. Is that the one? Yes. And do we have instances? We do not. Adjacency map is gotten from adjacency map.internal. Okay. Yes, we have instances here, and we can make a show instance. Can't we derive one? If we have show a, no, can't derive show. Okay. And that would be am of m and then show m. Right. And therefore this should now work, right? Yes. Okay. False with a link to false and true with a link to false. So that is not the fully connected graph. False is not connected to false, and this might be canonical actually. And so the adjacency map. How can I convince myself that two adjacency map actually will go to a canonical form? It folds over the graph with these constructors and adds and multiplies with the semi-ring. Is there a semi-ring instance on adjacency maps? There is, such that right, so this seems like it will enforce setness by making sure that we if we add edges and then we add the same, or add vertices and then the same, then they will end up being only one element in the set, and same thing for edges. Oh, interesting. With a different union for right, because multiplication needs to be a bit tricky. A map from A to set A. Right. Right. Because we need to treat, if we do map union with, then we treat vertices as keys. And so the question is, when we union with map, if we have the same key, then we union the values, which will union those sets. And that's the overlay. Just make sure that if we overlay two vertices that have potentially different edges, then we union their edges. But multiplication is going to use this IMAP union with, which is probably some kind of Cartesian multiplication, and that's from internal.map. Oh, that's here, internal.map, where we have unions with that takes a foldable of F. And we'll fold all we'll fold a container of maps, and the container of maps that we're asking it to fold is, where am I? I don't know, it's this. So we will do all the x and dy's, same as overlay, but it will get all the keys from y and all the keys from x and use from set on it. How does this work? It takes a k to an a and a set of k. So it takes all the keys from x, which is all the vertices from x, and it creates a set which I suppose what maps from k to a. Right, and it makes sure that all of the keys in x are mapped to all the keys in y's, right? And then that's sufficient. We don't need to do the other direction. Or it will depend whether those are directed or undirected. Like this is for directed adjacency graphs. So for undirected ones, it will be different. We will have to add the from set in the other direction. And do we even have that? We don't right now, I don't think, because I think from undirected we use the regular adjacency map. To adjacency map, we use the regular adjacency map. Oh, actually, we export to adjacency map in undirected for some reason. And yeah, in graph properties. So let's put it there. But it doesn't help. We need to create, I think, an undirected adjacency map, and we need to create a failing test for this. Let's create a failing test for this first. Undirected graph. Bool, say. So now I'm thinking that I'm treating an undirected graph as a directed graph that makes sure that edges go in both directions, but I'm not sure whether that's what I want to do, but we'll see. Adjacency map of simple Bool graph. Boolean graph. So we'll do undirected graph to adjacency map of, let's say, an edge between true and false connected to a vertex false. And we would want that to equal a map or rather an adjacency map which how shall we build it? How shall we build it from adjacency set? Don't like that. Transitive closure or symmetric closure, overlaying it with its own transpose. Yeah, that's what we'll end up doing, but yeah, I suppose there's laws here that we could test, that the symmetric closure of any undirected graph should equal itself. But yeah, so that's or is that the reflexive closure? No, that's the symmetric closure. Adjacency list. Did I even create a show instance for lists? I did. Yeah, to array. Getting a bit lost with the amount of graph types we have, and the fact that they're not a neat tree. There's some kind of lattice maybe. Right, so 2 indirected. Yeah, I'm not sure this even works. Or maybe it's fine because yes, it's just about how we reinterpret connect, in fact. But the interpretation of connect needs to go through the adjacency map. So so again, it is about 2 adjacency map here, but we need to create that test. And I suppose I can just, yeah, 2 agents. I can adjacency list of my adjacency map. I will get a list. I can show it. Is that what I want? Yeah, adjacency list. Actually, AM. And this will. Should I? So do I need to show it? I might. And I think I can do that. And then I say that it's the empty string for now. And okay, that should give me something to test. And that's pretty nice, actually. That's a nice representation to test. Okay, so what do we have here? We have false connected to false and true connected to false. And but yes, that's where we're wrong, right? Because in an undirected graph, that's true for a directed graph, but for an undirected graph, false should be connected to true. And but the truth is, though, that I think if I did the closure thing with the arbitrary instance, I will also get some of that. Meaning, I will have counterexamples such as this simple one. So it's an undirected graph is a symmetric closure of itself for a Boolean graph, because we're going to need to restrict the type. And then we're going to try to do the same thing we tried to do here, but we couldn't quite do, which is we want to generate 2 graphs. So let's try and see if we can do that here. Purescript, quick check, generate multiple values. Okay, let's look at a quick check here. Oh, that's move like that. Okay, prop. Can I make prop something that returns 2 graphs? I mean, maybe I can. Wow. Type inference, pretty amazing here. And equality doesn't hold. For the simple yes, the problem is that it's not going to give me the examples if I structure it like that. How am I is it an arbitrary? It's not equal. Oh, right. It's actually in spec. Oh, it's not a should, it's asserts. With help. There we go. That's what we need. And not hope for show H. And show G. We import this from quick check, and it doesn't parse. Oh, I see. Interesting. Well, I think this should work. It doesn't. Interesting. I see. Whereas assert equal gives us a result. So, there's also this. That's exactly the same one. You want a Boolean. What we want is more something higher order that I can pass a result to, but apparently you want a Boolean. So I think if I do equal equals, then maybe that will work. Yeah. Looks good, but it's yeah. So I can actually have something that's written a little bit in this style, which is what? Which is well, so G equals H. So right. Yeah. So I think in this case we have what? We have true and false. Is that right? Yeah, I think I need a little bit more. So what do we have? We have this. We have G, H, and I'll be right back. Okay, and again, my food is here, so I will be going for another 10 minutes. Put a clock on myself, as I like to do. Boom. Okay. Yes, so we were writing this such that it represents what we're trying to say, which is graph dot triple equals is different than well, yeah, ideally we want to know what that value is, right? So so we say, yeah, we say something a little bit different here. We say so we show G. We say with G this and H this. We say that show this is different than show this. And boom. All right, looks right. So that's a few examples. Don't know why we have a few examples now. Or is it because I have no idea. Because I show things, I don't know. So maybe, yeah, those are several counter examples, which is always good, I think. So yeah, false different from true. Maybe we should revert that so that it's easier to read. So we say false different from true. And this with another parents. And parents here. Let me say, separate those visually a little bit more. Yeah, I actually don't need this then. Nor do I need this. How's that look? False is different from true. If we want to do this in a way that looks just a tiny bit like this, there's spaces here, and where G is not G being this and H being that, we have inequalities, or actually this seems like it's even a simpler one. And yeah, so I think that's fine. What were we wanted to do the closures, right? So that was for indirection, and I suppose if I just take this quick check here and directed symmetric closure of itself for a simple Boolean graph. So I would say a bool and bool, and I would say that we take UG dot dot symmetric closure, if we can find it. Oh, didn't we? Oh, is it for adjacency maps only? Ah, it is for adjacency maps. Let's see. So how's that gonna work? Yeah, I think that's fine. So we say the adjacency map of the UG blah of the graph is equal to the symmetric closure of the UG graph, right? So how does that work? We say if that is a UG graph, and we say that adjacency map of G is equal to symmetric closure of adjacency map of H. I think, and that's Boolean. And we need UG dot adjacency map. And unknown value to adjacency map. And that would be AM dot symmetric closure, I believe. AM. And we're going to need some parents, I believe. And we don't have a arbitrary instance for UG graphs today, so let's create one. We haven't started on that. We were, or were we starting on that? No. Oh, but that's just UG fix gen graph. So that's easy. Arbitrary. Yeah, it's UG arbitrary, I think. Just need to import the thing, which is this thing. Right here. And yeah, right, so it's UG F mapped to arbitrary, is it? Yeah, I think so. And then is that gonna work then? It is. And what is our test saying now? A test returned false, and it's not giving me any examples. Okay. Suppose we're going to need to reuse this documentation trick here. So, okay. Let's see. It's going to give us a G and an H. Do we want the symmetric closure? I think we don't need to. I think we'll be probably fine only with the G and the H. So give me the G and the H, and let's see how we do. Oh, we need the show instance for undirected graphs, which should be simple. Can put it here. Show A, show graph A, show UG G, show G. And we can now show. Okay, plenty of possibilities here. G being blah blah, and oh yeah, I suppose that yeah, it's not two different graphs. We can't. That's a little bit of a hard test to pass. Okay. Trying to say that an arbitrary graph is the symmetric closure of any other arbitrary graph is of course not good. But here, well, true false. Interesting. True false. True false is already. Ah, yeah, because it's of course because it's undirected. And in fact, I need to yeah, I need to write the show instances differently. In fact, because this is actually directed here. And so I actually need to write my undirected graphs a la mano. And I could case here so that I don't have to do that. Case G off. Empty. Connect. And yeah, we need the arrow instead. And here we can put our bidirectional arrow. Yes, I believe these are the constructors here. And now we have to. So I'm generating an undirected one, so I expect that this will remain with the undirected things. And I'm generating different ones, which I suppose is fine. But that's what we'll fix next time. So let's write this down. I'm glad that we're writing property test. This feels right. So we've actually done one for undirected graphs, and then we're fix the symmetric closure equality law for undirected graphs. There we go. So that's it for now. Thanks a lot for watching, and I'll see you on Tuesday for more. And by the way, I'll be taking the second part of November off, but yeah, more about that soon. Bye bye.